All right, so welcome back to the OneClass channel. Again, my name is Joey. I'm going to be your math teacher for the following session. So, just a little bit about OneClass if you're tuning in for the first time. What we're doing here is we're going through a kind of a session of just verifying solutions for frequently asked questions by high school students and university and college students all around the world. So these are mostly focusing on subjects as in the mathematics and also in chemistry as well. So specifically today, what we're going to do is we are going to look at solutions and look at some questions basically for this hour. We have about 11 questions, and what we're going to do is we're going to look at these solutions that are coming from basically algebra 2 and pre-calculus questions. So much more kind of like senior level math in high school. So typically what we see probably about grade 10 to grade 12 math and calculus as well. So we're going to look at these questions for today. Again, my name is Joey. I'm currently a secondary school educator in Ontario, and what my teachable subjects are chemistry and music, but I'm also planning to get my mathematics teachable by September as well. So without further ado, let's get started on these problems. I have about 11 problems, so let's see if we can get through these guys here. So we ended off our actually previous video with this question. I never actually got to fully solve the solution for us. So I'm going to look at this one, and we're going to do this problem here. This problem is I would say it's a pretty tough problem, just because what we have here, it's not as tough as the Norman window problem that we were looking at before, because that one had irregular shapes. But this one is, again, kind of what you would see probably in a grade 12 calculus kind of setting. And what we're doing with this question is it's an optimization question. So when we figure out this optimization question, what we're going to do is that I'll show you the steps to kind of tackle these kind of problems with us. So it says for 10 marks, the top and bottom margins of a poster are each 10 centimeters and the side margins are 2 centimeters. If the area of the printed material on the poster is fixed at 50 centimeters squared, find the dimensions of the poster and with the smallest area. So we're going to check that the value obtained is indeed a minimum. So let me do this question for us. So I'm going to basically make a diagram here, make a rectangle here. And this here is our poster, and then we have margins of a poster. So we're going to have something that's slightly bigger, maybe even bigger than that. That looks good. So we're going to have kind of a poster, and then we have margins of a poster, right? So we can say that we have here top and bottom. So the top and bottom posters are this here. This is 4 centimeters. This guy here is also 4 centimeters as well. And then what we have here is the side margins are 2 centimeters, right? So these guys 2, and this here is 2 as well. Let me erase this. We're going to assume it's centimeters. Not assume, but I'm just going to write here it's centimeters. And then what we care about is if the area of the printed material on the poster is fixed at 50 centimeters, so the area of this inside here is 50 centimeters, find the dimensions of the poster with the smallest area. Okay, so let's solve this problem here. So what we're going to do here is I'm given the area here. The area here is 50 centimeters squared, right? So I'm going to write here 50 centimeters squared, or maybe I'll write the area here. The area of the total poster here, so I'm going to say area of the total poster is obviously going to be the area of this rectangle, right? And we know the area of a rectangle here is L times W or X times Y. In this case, I'm going to write here, I'm going to let this here be X. I'm going to let X be the width of the length of the poster, and Y be the width of the poster. What we can do is we can actually write an algebraic equation, right? I can say here X here is equal to this here would be X here is equal to I'm looking for the poster itself, so I'm looking for the area of the poster. This is the area, so this here is our poster, right? And then we know that the area of a poster here is going to be X here. If the total length here is X here, we can make an algebraic expression for if the total area here is X, and then maybe I'll do this in different colors actually. So if the entire length here is X, and this here is Y, the entire length of the poster here is Y, we can make an algebraic expression for just the poster, right? We can say that here this is here X equals, or we can say X is minus 2 times 2, right? Because I have this here side length is 2, and this side length here is 2. And similarly with y, I can say this is y minus, this would be 2 times 4, right? So I have some sort of area here. So I have an algebraic expression for specifically the poster here, right? Because again, the top and bottom here are 4 centimeters, and the side here is 2, right? So this here is our algebraic expression for this, and I can say that the area of the poster, or let me write this down. The area of the poster is going to equal, again, obviously the length and the width, right? So I'm going to say here it's x minus 2 times 2 here is 4, times 4 here, times y here, minus 2 times 4 here is 8, right? Which is that. So x minus 4 times y minus 8, and this is obviously going to equal 50 centimeters, right? Because I'm given a 50 centimeters squared here, right? So I have an algebraic expression for the poster. What I can do here is I can actually expand this and isolate for a variable here, right? So let's do that. So I'm going to rewrite this as 50 equals x minus 4 times y minus 8. I'm going to use FOIL to expand this. So if x times y, I have x times y here, so xy. X times negative 8 is obviously negative 8x. Negative 4 times y here is negative 4y, and negative 4 times negative 8 here is positive 32, right? So we have these couple of these guys here, and what we're going to do is we are going to isolate for one of these variables. We're going to isolate for probably y here, and the reason why we want to do isolate for a variable is because we're going to have to create another formula for us to optimize, right? We want an area of the entire poster here, which is probably x times y, right? We want the area of the entire poster, and what we're going to do is we're going to minimize that area. So let me isolate for one of these variables. I'm going to isolate y, for example. So we move 30 to the other side, 50 minus 30. I'm going to subtract 32 from the both sides. I'm going to get 18 on this side. And then get xy minus 8x plus minus 4y, sorry. And then I'm going to move 8x to the other side as well. So I'll have 18 plus 8x here equals xy minus 4y. And then what I can do here now is I can factor a common factor of this y, right? I know that 18 plus 8x here equals, I can factor of this y here. So I'm left with x here minus 4, and I can divide both sides by minus 4, x minus 4, right? So y here, I have my algebraic expression, which is 18 plus 8x divided by x minus 4 here. And this here is going to be my algebraic expression for y here. And what I can do now is I'm going to zoom out for us. And I'm going to look at, now, I'm going to write in blue here, and I'm going to write down the, I want to maximize a specific area, right? So I'm gonna put the area of the entire poster here. So the area of the entire poster is going to equal, obviously, x times y, right? X times y here, because this is the full length. I set the full length here as x, and the full length, or the width here is y, right? So it's going to be x times y here. And then what I can do is I can substitute my y value for this guy here, right? So I can substitute y here, and I'm only left with one variable. So that's why we isolated for a variable here, right? So we can say here a here equals x times 18 plus 8x divided by x plus 4. And then what I can do now is what I can do here is I can take the derivative, right? Because I want to take a prime here of x for us to solve to minimize our area, right? Because again, it says here, find the dimensions with the smallest area, which means it's an optimization question, which means I'm going to have to find the derivative of this guy here. So let me do that. So basically, I'm going to have a prime here. It's going to equal. So what I'm going to do is I'm going to do simply the product rule, right? I'm going to do the product rule for my derivative. So I'm taking the derivative of the first variable here, which is x, which is simply just 1 times x. So I can maybe I'll specify this for you as well. So I'm going to say product rule here. This is f of x, and this here would be g of x, right? So the a prime or the derivative is going to be f of x times the g prime of x plus the f of x times g prime of x, right? So we're going to have to do 18 plus 8x over x plus 4 plus, and then which is plus x times the derivative of this inside here. And if we want to find the derivative of this inside here, what we're going to have to do is we're going to have to to the quotient rule to figure out this guy here. I think what I'm going to do is I'm actually going to, instead of doing the product rule, because this looks like a lot of work, I'm going to actually factor in before I do the derivative. So let me just, I'm thinking about my kind of technique here, and I don't think it's actually the most effective. So I'm just going to put x plus 4 here. And let's see. I'm just going to go over and check my work here. X plus y minus x times 8 is negative. This is negative. It's positive. Okay, I think we should be good. Okay, so we have a prime here. What I'm going to do first before taking the derivative is I'm going to actually multiply this x in. So if I multiply this x in, I'm going to get 18x plus 8x squared all over x plus 4, right? So I'm going to have this here. And then what I'm going to do is I'm going to do my quotient rule. So I'm going to do a prime here equals. So if you recall from the quotient rule for our derivatives, what we're going to have to do is we have two functions here, right? So we have, you could think of this as our f of x, and you could think of this as our g of x, right? So you could think of, let me write this down for you. So you can think of this function as f of x. And this is g of x, right? So if we want to find the derivative of f of x divided by g of x, what we have to do is we're going to take g of x here, which is simply x plus 4. And then we're going to multiply it by f prime of x. So we're going to take the derivative of this top guy here, which is simply just 18 plus 2 times 8 here is 16x. And then we're going to minus f of x, which is 18x plus 8x squared, times the derivative of the bottom part, right? But the derivative of the bottom part here is simply just 1, right? The derivative of x plus 4 is simply just 1 here. So multiply that by 1. And then we put all over g of x squared. So I'm going to square this term here. So x plus 4, and then I'm going to square this term here. So this here, I applied my quotient rule to find the derivative here. And all I'm going to have to do here is I'm simply just collecting some like terms. And I'm going to set the derivative to 0 in this case for us to solve for the minimum here. So that's what we're doing. So let me set this to 0. I'm setting a prime to 0. And then what I'm going to do is I'm going to factor in and hopefully collect some like terms here. So again, I can FOIL x plus 4 and 18x plus 16x here. So foiling this, I would get 18x plus 16x squared plus 18 times 4 is 72 plus this is 64x minus, and then this is simply just times 1, right? So I can just simply write 18x plus x squared here. And then this is all over. This here is all over x plus 4 squared. So now I can collect some common terms here, right? So I have here 16x squared plus 8x squared. So I'm going to have 24x squared. I'm going to do this back in, yeah, I'll do this in red. Actually, no, I'll do this back in blue. So 24x squared. What other terms I have here? I have 18x, 64x, and minus 18x, right? So I'm going to say 18 plus 64 minus 18 here, which is simply just 64, obviously, because these two guys cancel out. So I'm going to have plus 64x. And then all I'm left here is this 72, right? Plus 72 here. And this is still all over x plus 4 squared here. So again, what I can do now is I could either, and this here I can set to 0, right? And this is obviously set to 0. What I could do is if I want to kind of expand this guy here, I would actually factor out the top here, right? I would factor out the top to see if I can actually get some type of common factor here. So in order for us to factor at the top, I'm looking at these guys here. I think they're all divisible by 8. So I'm going to take out 8 here. I'm going to get 3x squared plus 8x plus, I believe this is 12, all over x plus 4 squared. This here now, I'm simply just factoring this top part here, right? So I can do decomposition. So 3 times 12 here, product of 3 times 12 has to add up to 8. So 36 has to add up to 8. Let's see. I don't know if this is actually factorable. So yeah, I don't think this is actually factorable. So what I would have to do is, let's see, if this top part isn't factorable, then I would basically just get, let's see, because I'm trying to cancel out this top and bottom part to solve for 0 here, right? So I might have to actually backtrack here. And this here was 0, right? I might have to expand this to see if I can factor out something from the top and the bottom here, just to figure some stuff out. So let me do that for you real quick. So then I guess I won't factor this part, or I'll keep the factor here, and all I'm going to do is this here is 8, 3x squared is 12, and then if I factor out this is a perfect square trinomial. Obviously, I'm going to x squared here plus 8x plus 16 here, and let's see. I don't know if I can cancel these two terms out here. But if again, because I'm 8 here is a separate term here, I can cross out. I can divide out these two terms to get 3. I can cross out this 8 term here, and this 12 is simply just 12 over 16 here. So let's see. Because I don't really want my x's to cancel out here. So let me just think about this problem here. 1 minus 1 here is still 0. So these guys again cancel out here, which is no good. And I'm left with just simply numbers here. That's no good. So I have to somehow solve for my x. So I'm just going to look back at let me see if I did my quotient real correctly here. Just to see if I did the right here. I have g of x here, which is 8x plus 4, times the derivative of this, which is 18 plus 16x, which is great, times, minus 18x plus 8x squared times the derivative of g of x, which is 1 times x plus 4 squared. So I should get something like this. Let me see if I fold correctly. X here would be 18x. This would be 16x squared. This here would be 18 times 4 is 72. And then 4 times 16 here is 64. Minus 18x plus 8x squared. Yeah, so that should be okay. These two guys cancel out. I get 24x squared plus 64x here plus 72 times this. So I think my math here is good. And then I'm just going to set this to 0 to basically solve for my x value here. Yes, I'm basically solving for my x value here. So I'm basically left with this guy here, right? So this guy here is, or actually I don't even think I should factor here. I think I should just leave this here. So this here would be our kind of like the most math we can do to simplify this problem, right? So basically what I'm left here with this here, I have 0 on one side and I have something divided by 0 here, right? So basically what I have to do is if I want to solve for the 0 here, I'm going to say that this here times what number here equals 0, right? I can set these two terms to equal some type of 0, right? So I can say here that that x plus 4 here is going to equal 0 here. I can set this to 0 because if I'm going to multiply this number by this number, it has to equal 0, right? So one of these guys has to equal 0 here. So I can set basically this top part here to 0 to see if I can solve for something here. But I believe that I don't think it's actually factorable. 3, 5, and 8 will give me a complex number here. So if I get a complex number here, then I would have to simply just do, I have to set x plus 4 here to 0 to solve for something. So So let's see. I'm going to solve for x plus 4 here, which equals to 0. So therefore, x has to equal negative 4 here. But negative 4 doesn't make any sense here because I have a negative length, which does not make sense here. So let me just go back to... Oh, that makes sense. Okay, I know where I messed up here. I put in x plus 4 instead of x minus 4. Yes. So this should be minus 4. This is minus 4. This here is minus 4. And this here is minus 4. Okay. Okay, I think we're good here. So basically I have, let's see, x minus 4 squared here would be, again, a perfect square trinomial. I can say x minus 4. So I copied the wrong problem. Sorry, x minus 4 and x minus 4 here. I can expand this to get x squared minus 8x plus 16. So I can write that down here, right? So hopefully there's terms that would cancel out here. Divided by x squared. This here's x squared minus 8x plus 6. And these two terms would now cancel out, right? So again, simply just divide out here. So again, these two terms, these x's would cancel out here. And then I believe that the x's will also cancel out here. So that is actually no good again. So what I would do here, let's think about this problem here. So again, because the x's here cancel out, I can't actually, this doesn't make sense here. So what I'm going to do here is I have x minus 4 squared here. And again, I'm setting this entire equation to 0, right? So again, here x has to be greater than 4 here, right? Because again, my denominator here cannot be 0 here. So if it can't be 4 here, then I'm basically going to set here x minus 4 here squared here. It's going to have to equal, again, my area here, which was 50, right? 50 here. So I'm going to solve for this solution here. So solve for x here. So again, I have x minus 4 squared equals 50. I can square root both sides to get x minus 4 is equal to root 50. And then finally, x here would equal root 50 plus 4 here. If I want to simplify it to radical, to get rid of the radical here, I would get simply something like this. And then I would get 5 root 2 plus 4 here. And this here would be my x value for the total length of the poster. I'm going to just do that in decimals for you so you get some type of value, which is 11.07 or 11.1, I think. I think they want it in the nearest decimal. So if x here equals 11.1, then I can simply just say I can solve this back for this AT here. And this total area is going to equal, again, or I can solve for the area of the poster here, right? So I can use that to solve for the area of the poster. And this here is going to equal, or I'm going to use this equation, sorry. I'm using this equation here. So 50 here equals x here, which is, x here is 11.1, I believe. 11.1, sorry. So here's 11.1 minus 4 times y minus 8. 11.1 here minus 4 would equal 7.1 times y minus 8. Again, I can factor out, or I can expand to get 7.1 times negative 8 here, which would be negative 56.8. And then I'm running out of space here, but that's okay. I add both sides by 56.8 to get 106.8 equals 7.1y. And then I can finally divide both sides by 7.1 to get my value, which is 15.04 here. So 15.04 here would be the length of the poster. So again, my dimensions here are simply 11.1 here and 15.4. So therefore, after all that math here, first big question, our dimensions for the smallest area for poster is, and then you're right here, 11.1 centimeters by 15.04 centimeters. And this here is our solution. And again, this here is definitely an incomplete solution. They did nowhere as much work as I did here, but this here gives us a good kind of grasp as to what we're doing here. Again, it took me half an hour to do this problem. The optimization questions usually take a lot. It's because I messed up here. I didn't copy x minus 4 correctly, so that's totally my fault. But we could have done this problem much faster if I didn't make that mistake here. But what we're doing here is, again, we're setting an algebraic expression for the poster. We're finding an area of the rectangle. We're isolating for a variable, and then we're substituting it into another area formula, right? So we have the area of a poster, and then we have the total area here. And we're given an area of the poster first, so we can solve for a variable here. And what we're going to do is we're simply just plugging in this y value for a direct substitution here to solve and then take the derivative to minimize the area of the minimize the area, right? So that's what we're doing in this problem here. Actually, I think the dimensions of the poster, or is it the total area is 11.504. Sorry, I think I messed up here again. But 11.1, I'm gonna have to actually I'm gonna have to subtract the borders to that, right? So again, because the area of the poster is x minus 4 here, so I'm gonna have the area of the poster, because this here is the total area, not the area of the poster. The total area would be 11.1 minus 4. 11.1 minus 4, which is 7.1. So it's going to be 7.1 by whatever 15.04 minus 8 here is, which is 15.04 minus 8 here is 7.04. And this here is my answer. This here is the solution here. 7.1 by 7.04 here is my answer here, because this, again, the area of this is going to equal 50, or approximately 50. So this here is the correct answer. This here was not dimensions of the poster. This is dimensions of the total with the margins here. So this is with the poster with margins. And this here is let me clarify this. This here is the dimensions for the poster. So I forgot to substitute back in of poster. So this solution here is incorrect. Obviously, they didn't show any work. Is incorrect. Did not show any work. And the correct solution is 7.1 centimeters by 7.04 centimeters for the dimensions of the poster to have the smallest area here. Okay, so the solution here is incorrect. Okay, we took a lot of time to do one problem, but that's okay. We would have done it a lot quicker if I wrote x minus 4 squared instead of x plus 4 squared, so that's totally my fault. But hopefully we can get through the other questions as well here. So number 2 is asking us if the measure of a central angle IJK here is pi radians, find the area of the shaded sector. So let me redraw this guy here. And I have a line here. Let me use the line tool. And then I have here I, J, and then K. And the IK, we know the IK here is 4 units here. And I want to find this shaded area, right? I want to find this shaded area here. And the measure here is pi radians. So find the area of the shaded sector. So what is the area of the shaded sector? So again, very, very easy here. In order for us to do this problem, what we know here is that we know the area of a circle here is pi r squared, right? So area equals pi r squared. And in this case, we want only the area of half the circle here. So we're taking the half of the area here. So half would be, area is half pi r squared, and we know that our radius here is from j to k, right? Here, this guy here is our radius. So this guy here is our radius, but then from I to k is 4 units, right? So if it's 4 units, we would simply divide this by 2 to get our radians, which is simply just 2. And then now what we can do is solve for the area, right? So we can say a here equals half times pi. We know our r here is simply just 2 squared. A here is half times pi times 4 here, right? 2 squared is 4. And then finally, half times 4 here is simply just 2. And we leave pi as is. So a here equals 2. Option A is correct. That's good. It's because we're given the diameter of IK is 4 units. So therefore, divided by 2 is 2 units, right? So r here equals 2. The radius here equals 2. That's a really bad r, sorry. Radius here equals 2. And then all we can do is we can simply just use a equals half pi r squared, and we can take the half of that to find the area of the semicircle. So therefore, this would give me 2 pi here. So solution here is correct. Good analysis here. Okay, number 3 is asking us a water balloon is catapulted into the air from the top of a building. The height hx in meters of the balloon after t seconds is h of x at -5t squared plus 30t plus 10. What are the domain and range of this function? When will the ball reach a height of 30 centimeters? So this is a 2-part question. So let me write this down first. So I'm gonna the A is asking us domain and range, right? Domain and range. And then B is asking us time at height equals 30 centimeters. I'm using h here as height here. So now let's do the domain and range first. So I'm given the function here. We're given the function h at x equals -5t squared plus 30t plus 10 here. And we're looking at what is the domain and range. Well, if you look at the domain range, I'm taking a look at this function here. What we can do is we can solve for it either graphically or we could solve for it algebraically. In this case, we'll probably do an algebraic one, just because, again, I could graph this as well using Desmos or something like that, or I could basically solve for the intercepts and also the graph, right? So let's solve for this here algebraically. So again, if I have h of x here, what I can do is I can take out this -5. I'm going to common factor first to get t squared minus 6t minus 6. And then all I'm left here with, I know here by inspection, t squared minus t minus 6 here, I can factor by inspection here. And this will get me, let's see, 6 times 1. Let me see if this is factorable. I'm pretty sure that this here is factorable. 1 minus 6 here would give me, I would have to actually use quadratic formula to give me the intercepts here, because it's actually not factorable. I thought this was a 5 here, so it's not factorable here. So what I can do here is I can use a quadratic formula to solve for this, to solve for the x intercepts here, but that might take a lot of time. So let me just, I think for the sake of time, what I'm going to do is I'm going to actually show you a graph of this function here without, and then kind of do that. So let me just skip the steps for the quadratic formula. I'm pretty sure you folks at home know how to use the quadratic formula already. And basically you get here x minus 6.873, and then you get here x plus 0.873 here. So you get these two x intercepts, and again, I rounded here. So what we can do is we can actually, we can use these intercepts to kind of like graph this, right? So we can graph this, or maybe sketch a graph here. So we can sketch a graph here. And we can say that, again, this is y, this is x here. And we know that x intercepts here, we have our 6.873 here. So I'm going to say this here is 6.873. And then we have also a graph. Here it's 0.873, and we know that our parabola is going to open. It's going to open upwards, right? I have a negative a value here, so it's going to open. Basically, it's going to do something like this. So this here is our sketch. Again, we can also solve for the vertex here very easily by simply just taking the equation of the axis here, so dividing these two guys by 2, and then substituting it into the equation. So let me just do that for you to solve for the vertex here, right? So again, I have 6.873. I'm going to add that by add that to negative 0.873 to get, again, a value of 6. I divide it by 2 here. It's going to be 3. So therefore, at at 3 here is going to be my vertex, right? So I'm going to plug h of x at h of 3 here to solve for the height. So negative 5 times 3 squared plus 30 times 3 plus 10 here would give me a value of 855. So this here would be 855. And this here would be the vertex of my parabola. So understanding this, and we solve for this, and what we can do is we can actually, let me just use Desmos to verify this for you. And what we can do is, once we get this graph here, we can solve for the domain and range, right? So let me write here, this is negative 5. I'm going to write x squared instead. And then plus 30t plus 10t here, or sorry, x, not t, plus 30t plus 10x here. And as you can see, our parabola looks something like this, right? It is very, very, very large here, and it's going to span to about 80. Oh, I don't know why it's 855 here. This is not 855 here. The vertex here, I think I might have done my math here incorrectly. 4 and 80. Oh, yes, it's actually 4 and 80. Sorry, not 3 and 80 here. I think I messed up my math here. I'm supposed to add both guys here. So it's 6.873 plus 0.873 here, which will give me a value of about 7.876 here. So let me just check my x-intercepts for us here. Negative 5. Here I have negative. Okay, sorry. Oh, so I think I graphed this wrong. Sorry. So I'm gonna write here because I'm graphing this guy here, right? So this is t squared here times negative 6t. Oh, this is a 10, not a 6. Oh my gosh, I'm all over the place today. This here's a 2. Sorry, folks. I don't know why I wrote a 10 here. Okay, so this graph is wrong. Oh no. My fault, guys. I'm off my game today, but that's okay. So basically what I have to do here is, again, I have t, yes, here. I have negative 5. So negative 5, I factor that out, I get negative 5 times t squared minus 6t minus 2, right? So 1, negative 6, negative 2. I can factor that, I get 6.3. So if I were to factor that, I would get t would be 6.317, and this here is positive 0.317 here. So again, this is simply just done through quadratic formula, and the negative 5 is here. And again, I can always graph this, and I would basically get the graph that I saw at Desmos. So let me just write that for you here. 5x squared plus 30t plus 10, right? Yeah, plus 30x plus 10x plus 10 here. So again, you get two x-intercepts here. You get one here at 6.317, like I said here, 6.317, and then one at 0.317. And again, what I can do is find the vertex here simply by adding these two numbers and finding the average of these two numbers, right? So I can say here 6.317 minus 0.317 here is going to give me 6. And then I'm going to divide that by 2 to get me our vertex here, which is going to be at 0.3, right? It's going to give me 3 here, right? So again, I'm using the equation of the axes to basically finding the average, right? 6.317 plus negative 0.317 divided by 2. This is 6 divided by 2, which equals 3. And then I can basically substitute in h at 3, right? I can say h at 3 would equal negative 3 squared plus 30 times 3 plus 10. This here would equal negative 5 times 9 plus 30 times 3 is 90 plus 10. This here is negative 45 plus 90 plus 10 here, which is simply negative 90, which is, let's see, negative 45 plus 90 plus 10 here would give me a value of 55 here. And 55 here is the vertex, right? As solved here as well. So once we're given the vertex here, why do we care about this vertex? Well, we care about this because we're finding the domain and range, right? So we care about this because we want the domain and range. So let me do the domain first. So domain here is indicated by the x here equals all real numbers, And this is just a notation to be right here. X belongs to a set of real numbers, and the X here, if you take a look at this X here is going to be all real numbers, right? Again, I can extend this all the way to here, -35 or something. I'm still going to get some type of value. I can extend into positive infinity here. I'm going to get some y value here. So I can say X belongs to a set of real numbers. And there's no restriction on this X here, right? So this is it. But the range here, again, y belongs to a set of real numbers. And y here, again, I have this vertex here. This vertex is so important because above this vertex, I don't have the function anymore. So this function has to be, y has to be either at 55 or lower or below 55, right? So you can say here, y has to be either less than or equal to 55. So this here is my domain range for this function here. So that was part A. And then part B was asking, when will a ball reach a height of 30 centimeters? So again, because this is in meters, right? So we actually have to convert 30 centimeters into meters first. So 30 centimeters is going to equal, if I want to convert this into meters, so 1 meter is 100 centimeters. These centimeters cancel out, so 30 divided by 100 is simply 0.3 meters here. So I'm going to get h at h basically is height, so which is going to be at 0.3 here, equals -5t squared plus 30t plus 10 here. And then I can simply move 0.3 to the other side, so 0 equals -5t squared plus 30t, and then moving that to the other side would give me positive 9.7 here. And what we can do here is we would basically have to do quadratic formula. I don't think I can factor this out. So again, for the sake of time, I'm going to actually I'm going to show you what the answer is, but you can write down basically t here equals -b plus or minus the square root of b squared minus 4ac all over 2a. Negative here, 30 here is -30. Negative b here is -30. Plus or minus b squared here is 900. Minus 4 times -5 times 9.7 here. Again, I'm kind of speeding through this just because, just for the sake of time here. But yeah, I'm pretty sure we know how to use the quadratic formula. Plus or minus, again, the square root here would be 900 minus 4 times this is -5 times 9.7. This here would give me a value of 1094 all over 2 times -5 here is -10. So therefore, I'm going to get two answers here. -30 times the square root of 1094 divided by -10. And this here is -30 minus the square root of 1094 here. Square root of 1094 divided by -10. So these two here are my answers for the t values here. And then basically I'm going to sub this into my calculator to solve for something. And usually one of these guys here is going to be negative. And again, I can't have a negative time. So I'm basically just going to cross out that answer and basically take the other one here. So again, this here is my negative answer. I get -0.307. And this would be in seconds. And this here, I would get a value, I should get a positive value here of 6.307 seconds. And again, because I can't have a negative time here, I can say that I can reject this answer. T has to be greater or equal to 0. So therefore, 6.3 or 6.3 seconds here is my answer. And if you look at here our graph here, we can take a look at where 6.3 is and figure out where it is at 30 centimeters, right? So if I'm looking at the graph here, I'm looking at where is this graph 0.3. So let's see, 0.3 would be either 0.3 would be either at this point here. This point looks like 0.3. So again, this was the negative 0.37, or it would be all the way here, right? 0.3 would be about here. Again, 6.37 here, which is about 6.3 seconds here. So this solution obviously is incorrect. They didn't show me any work here. And I'm going to write down here domain of function here is x belongs to a set of real numbers. There's no restrictions on my x. Range of function is y belongs to a set of real numbers as well. And y had to be, let me just look at my answer here. Y had to be greater, or y had to be less than, or y is less than or equal to 55. And then finally, the ball will reach a height of 30 cm at 6.3 seconds. Solution is incorrect because it is an incomplete solution. Okay, solution here is incorrect. Okay, so that was number 4. I think I'm only going to do like 5 questions today, unfortunately, just because the first one took so long. How do you find the value of cotangent pi over 2? Is it pi over 2 or just pi 2? I want to say it's pi over 2 here, but let me just write down. I want to find the value of cotangent pi 2 or 2 pi, because then and maybe some formatting issue here, but because usually you would write cotangent 2 pi and not cotangent pi 2, but they might have referred to pi over 2. So actually what I'm going to use is, let's just solve for both and see which ones we get. So I'm going to assume that this here is 2 pi, or this would be pi over 2 here. So when we look at this here, cotangent 2 pi here, what we can do to solve for these guys here is you have to use the trigonometric ratio. We can think of it as we're using the cast rule here. So let me just draw this out here. And we know that this is the all, this is C, this is S, and this is T, right? So cotangent, you can also rewrite cotangent as, remember, we know that this here is 1, a cotangent here is simply just 1 over tangent, right? So you can simply rewrite this as 1 over tangent of 2 pi here. And we know that 2 pi here is here, right? Again, this here is 0 and 2 pi. This here is pi over 2. This is pi. And this here is 3 pi over 2, right? So tangent 2 pi here, it belongs to here, right? It belongs here. So tangent of 2 pi would be 0, right? Again, I don't have anything here. This here is 0 here. So which means 1 over 0 here, cotangent 2 pi, cotangent 2 pi would be 1 over 0 here. And this is actually an undefined thing. So this here is undefined. So it equals 1 over tangent of 2 pi, which equals 1 over 0, which equals undefined. So if the problem was asking what's cotangent of 2 pi, this would be undefined. However, if it was asking for cotangent of pi over 2, which is here, cotangent pi over 2, then you can simply say that you can, again, rewrite this as tangent or cotangent. Cotangent is 1 over tangent of pi over 2. And again, wait, no, pi over 2 for tangent here is equal to 1, right? So this equals 1, and therefore the answer here is 1. So I don't know what they're trying to do with this problem, but they wrote here it was 0, and this solution here is actually incorrect because again, tangent of 2 pi here, tangent of 2 pi is 0, but cotangent of 2 pi here is 1 over our tangent here, which is undefined because you can't divide anything by 0 here, right? So let me just let me show you a chart here of how we know this here. So again, cotangent is simply just 1 over tangent, right? The same with sine. Cosecant here is 1 over sine. Cosine is or secant here is 1 over cosine, and cotangent would be 1 over tangent here. They're just the you can think of them as the reciprocal kind of trigonometric ratio here. So reciprocal like trigonometric ratios would be there. So again, 1 over tangent would be, again, this answer could either be 1 or 0 depending on how they were to format the solution. So I'm going to say the solution here is incorrect. So cotangent 2 pi equals undefined because cotangent 2 pi would equal 1 over tangent 2 pi, which equals 1 over 0, which equals undefined. And then if it was cotangent pi over 2, it would be equal to 1 because because 1 over tangent, or sorry, cotangent pi over 2 equals 1 over tangent pi over 2, which equals 1 over 1, which equals 1. So the solution here is incorrect. And then finally, I guess I'll do one more question and we'll wrap it up here, just because I guess I can only do 5 questions for today, just because the calculus one took so long. So I apologize for that, and it's because it was a mistake on my part as well. So it says here, which represents the graph of linear inequality. So I'm not given a graph here, so they didn't really attach a file here. So maybe I'll just maybe what I can do is I can graph it for you. That might be a bit better. So this is 6x plus 2y is greater than negative 10 here, right? And as you can see here, they give you the solution here. So basically what they want to do is they want to rearrange this for y, right? Because again, you can think of this as a slope standard form of a line. We want to rearrange to get the slope intercept form, right? So I would divide basically both sides by 6x. So we get negative 10 divided by 6x. And then finally divide both sides by 2, right? So I would do y here would be negative 10 over 6x divided by 2. Let me just clean this up first before we actually do this. So this is negative 6x, so 2y would be negative 10. Negative 10 divided by 6 would be negative 5 over 3 here. X, and then I can simply say y has negative 5 over 3 x divided by 2, right? And this here is going to equal this here. See what they did here. They divided everything by 2 here. So they divide by 2 first, which actually I think it cleans it up a little bit nicer than what we have here. So let me redo my algebra here, and I think I like the solution better than what I did here. So basically they divided everything by 2. Oh, here to get 3x plus y is greater than negative 5, and they just simply threw negative 5 plus 3x here. So this here would be, minus 3x here. This here would be our slope intercept form, or you can say y here is negative 3x minus 5 here, and you can graph this, and we can graph this very, very easily. What we can do is, again, we can draw a line here. Let me just sketch this graph for you quickly. So we have, again, this is our x, and this here is y. Negative 5 here is going to be our y-intercept, right? So I can say here this would be negative 5. And then my slope here is negative 3, right? So basically my line is going to point downwards like this, and then it's rise over run. So basically I'm going to go down by 3 and then go to the right by 1. So down by 3 would be like negative 8 or something. Right by 1 would be, this would be 1 here like that. And then I can also go up and say this is negative 2 here, and this would be negative 1, so maybe something like this. So I would get a line that looks something like that, and this would be my line for this inequality here. Now, as you can see, this here is an inequality like so. Again, we could solve for the x-intercept as well if I wanted to be a little bit more concise here by simply plugging in 0 and solving for the x-intercept. So I can do that for you. Plug in 0, I would get negative 3x minus 5. And x here would equal negative 5 over 3, right? Which is this guy here, which is supposed to be this point here. But I don't know if I sketched it nicely enough to get that point. But that's kind of our graph for the inequality here. So this here is negative 5 over 3 here. So this solution here is correct. Again, they did the graph here, which is great. So the solution here is correct. Good analysis as well. So that's going to be enough for today. Again, I'm so sorry for that first problem here. I kind of got thrown off when I threw off my game here when I forgot a simple negative sign instead of a positive sign. So I apologize for that little error that I did there. Again, if you like these videos, again, thank you so much for watching. Thanks for tuning in. You can always find these videos reposted on our YouTube channel at youtube.com/OneClass. Again, my name is Joey. It's been a pleasure working with you all. Again, you can catch me streaming basically Monday, Wednesdays, and Fridays for mathematics, and Tuesdays and Thursdays for chemistry. So, as always, thank you so much for watching. Stay safe, stay healthy, have a great day. Take care.